So, today we are going to complete our discussions on the Quasichemical approach of phase diagrams. I think in the last two lectures I described to you how we can derive the expression for the enthalpy and entropy from the atomistic viewpoints. So, I will just try to first correlate that things, and finally we go ahead with the free energy formalism. So, as you know, the important aspect is this parameter for any stability of phase, that is called the free energy change, delta G. Delta G is nothing but change of free energy when you add two elements together to form a solid solution or liquid solution, and delta G is equal to delta H minus T delta S, where delta H is the enthalpy change and delta S is the entropy change. So, delta H as I derive is basically Zn multiplied by Xa 1 minus Xa Hab minus Ha plus Hbb divided by 2. This is what is the expression for delta H. Sometimes people write this is equal to delta Hm because it is a mix. Similarly, this is delta Hm and delta Sm, but it is not important, you can use without superscript also. Similarly, delta Sm I have derived to be minus n k Xa ln Xa plus 1 minus Xa ln means log of 1 minus Xa. Okay, so thus delta Gm will be equal to Zn Xa 1 minus Xa multiplied by Hab minus Haa plus Hbb by 2 plus T into n k multiplied by Xa ln Xa plus 1 minus Xa ln 1 minus Xa. That is the whole free energy change when you form solid solution using two atoms A and B type. So, as you can see here, this term is called entropy change and this term is called enthalpy change. So, let us first discuss one by one what will happen the situations. Entropy change, that is T n k multiplied this term, is always negative. Why? Because Xa is always a fraction, and because Xa is a fraction, so 1 minus Xa is also a fraction, and due to that if both these two parameters are fractions, then log of a fraction is a negative number, like log of 0.5, log of 0.4 is a negative number. Because of that, this term is a negative term. Obviously, n is the Avogadro number, k is Boltzmann constant, it is the temperature, they cannot be negative. So, this is negative means this whole thing will be negative. As you know, the free energy change for any spontaneous process should be as low as possible and it must be negative also. So, therefore, for the Gm to be negative, this is already negative. If this term is negative, then delta Gm also be negative. What I mean to say is that if Gm has to be negative, then this term must be negative, or this term must be positive but lower than the value of this term, because this is always negative. So, let us be very clear about that, as the delta Sm term, T delta Sm term is always negative. So, for this to be negative, delta Hm to be either negative or less than T delta Sm term. That is very clear. If that is the case, then solid solutions will easily form. So, now if I take delta Hm term, it depends on what? It depends on again these fractions Z and N and this factor. Now if you look at carefully, Z is the coordination number, that is a positive number, N is Avogadro number, that is a positive number, Xa and 1 minus X are also positive numbers. Therefore, whether delta Hm will be negative positive, that depends on the sign of this factor inside this. What is that? For delta Hm to be negative, the factor which will control it is this one. This factor will be controlling whether it is a negative or positive, this factor. What is that factor? This is the enthalpy of AB bond or bonds formed by opposite atoms or the different atoms minus the average of the enthalpy of the AA bonds or BB bonds, that is similar atom bonds. So therefore, this is nothing but difference of the enthalpy of this dissimilar bond energies minus enthalpy corresponding to average enthalpy corresponding to similar bonds. So therefore, the whole sign will depend on relative values of these factors. Depending on relative values of these, there are 3 different situations possible. The first one, which is case 1 for your case, case 1 is what? Case 1 in which HAB is equal to HAA plus HBB by 2. That means this whole thing is 0. Why? If the bond energies of dissimilar bonds is equal to the average of bond energies of dissimilar, bond energies of dissimilar bonds equal to the average of the bond energies of similar bonds, then this term will be 0, this will vanish. If this vanishes, delta Hm will also vanish, that means delta Hm will be 0. I think I would like to clarify you one thing before I go ahead. I am always correlating these H terms, enthalpy terms with bond energies. As you have seen in my formalism, these enthalpy terms are directly related to the bond energies and also number of bonds, correct, because enthalpy is related to the bond energies and the number of bonds of that type present. So therefore, I am relating these enthalpy terms with the bond energies. There is a direct correlation, this is very clear. So the first case, if the enthalpy of the dissimilar bonds is equal to the average enthalpy of the similar bonds, delta Hm will be equal to 0. If delta Hm is equal to 0, then delta Gm is nothing but this term T n k Xa log of A plus 1 minus Xa log of 1 minus Xa, okay, and this is always negative, always negative. So for that case, this is the case of ideal solution. That means what? For any value of temperature and Xa, this is delta Gm and this is Xb or Xa, suppose this is 1, this is 0, this will be, the curve will look like this. So that means for any value of Xa, any value of Xa, temperature, whatever may be, the solution will be stable always. It does not matter whether the temperature is low or high, the concentration of A is low or high, it does not matter at all. This is the situation for ideal solutions. That is why ideal solutions are always stable at any temperature and any concentration of the elements present. So this is the case 1. This normally does not happen in the real situation. In real situations, bond energies of the dissimilar bonds will not be always equal to the bond energies of the average bond energies of similar bonds. Okay, now let us look at the case 2. What is case 2? Case 2 is the one in which this one is less than equal to this. I put mod because normally bond energies are negative, normally, or in the chemistry literature you see bond energies are considered to be negative. So, that means if the bond formed between AB atoms, the energy of the bond is always treated to be negative. So, that is why I have used a mod values. So, now if this is a situation, if suppose delta, if suppose the HAB energy, bond energy is less than the average bond energies of the HAA or BB and AB, okay, or otherwise HAB is less than or equal to HAA BB by 2. If this is the situation, what will happen to this term? This term will also be negative, because HAB is negative, as by convention bond energies of any bond is negative. So, that means if HAB is negative and less than this value, then whole term will be negative. So, thus in that situations, if that is the situation, what will happen? In that situation, you will always have AB bonds will be preferred, but it has low energy. If AB bonds preferred means what? The dissimilar bonds are preferred, and dissimilar bond preferred means you have ordering. What is the meaning of ordering? Okay, let me be clarified. You know, ordering means A atom will always like to be surrounded by B atoms, or B atoms will like to be surrounded by A atoms. Okay. So, that is the ordering. It will be never that A atom will be surrounded by A atoms or B atom will be surrounded by B atoms. It will be always the case that A atom is surrounded by B atoms, or otherwise B atom is surrounded by A atoms. That is nothing but ordering or superlattice formations. This is the situation for the most of the intermetallic compounds we discuss, intermediate compound we discuss, like NiAl, Ni3Al, FeAl. There are many intermetallic compounds I have discussed, intermediate compound to discuss. For that, this is the situation. The bond energies for AB is lower than the bond energies for the average bond energies of A and BB. Is it clear? But whatever the situations, these will be negative, and because this is negative, delta Gm is also negative, and delta Gm negative will be giving you the stability of the phase. So, that is why actually in this case also, if I plot A Gm versus Xa, this will be also like this. Okay. But for the most of the intermetallic phases, because they are stable only for a small composition zone, the free energy curve will be like this. Suppose this is 50-50 substitution of nickel aluminum, so intermetallic compound. So, this is the 50-50 compositions, and it is clear that this can accommodate some stoichiometric differences. So, therefore, the free energy curve will be looking like this. Similarly, for Fe3L, suppose for Fe3L it will be different, it will be 2:3, 2:1 or 3:1. So, therefore, positions will be different. So, my real intention of this is that for formation of order compounds or superlattice compounds, this condition to be satisfied. So, this is case 2, okay, not case 1, case 2. Now, the case 3 is the most interesting case. Let us discuss that. Case 3 is the most interesting case in the sense that in case 3 we get a situation like this. Where the absolute value of HAB is higher than the average value of HAA and BB in absolute, that is in mod. Okay. What does it means? This value is greater than these two, that means this term will be positive. Okay, this term will be positive, and if this is positive, then delta Gm value will depend on whether this one, the enthalpy contribution is higher than entropy contribution or not. If the enthalpy contribution is higher than the entropy contributions, one situation will arise. Otherwise, if suppose although this is positive, this enthalpy contribution is positive, but the value is lower than the entropy contribution, then it will not change much. It will be same as what I have seen earlier. What I mean to say is that delta Gm to be negative, this to be either to be negative, or because the entropy contribution is negative, this can be positive, but the value of this part will be lower than the value of the absolute value of this part will be lower than the absolute value of entropy contribution. In that situation also, delta Gm will be negative, correct. So this can give to two cases. Case 3a is the one in which delta Hm is positive, but the contribution of delta Hm is much lower than T delta Sm, correct. So that means T delta Sm term will be over or will be much higher than the delta Hm term, and this will be playing the main role. In that case again delta Gm will be negative, so therefore solid solutions or liquid solutions will form. But in case 3a, 3b, if delta Hm is positive and higher than, and this value is higher than T delta Sm, then delta Gm will be negative, positive, because this is positive, and its value is much higher than this, then delta Gm will be positive. Okay. So if that is the case, then there will be a problem. Okay. Now let me tell you what is the real aspect of the situation. If the bond energies of dissimilar bonds, enthalpy corresponding to dissimilar bonds is higher than average values of enthalpy corresponding to similar bonds, that means what? These bonds, similar bonds are preferred. A atom will like to be surrounded by A atoms, B atoms will like to be surrounded by B atoms. This is known as typically clustering in the situation. This situation is known as clustering, correct. So clustering will happen. What is the meaning of clustering? That means you have segregated regions in the solutions in which A is surrounded by A or B is surrounded by B. It is very different from the last case in which I said A will be surrounded by B or B will be surrounded by A, that leads to superlatives or ordering, but here it is opposite, A is surrounded by only A, B is surrounded by only B. That is known as clustering or segregation in the literature. And although this clustering or segregation will happen, but depending on the absolute magnitude of A delta Hm and T delta Sm, these two situations will be possible. So case 3a is need not to be discussed because this is similar to the last case. Case 3b is what we need to discuss. Case 3b is what is we need to discuss. Okay, so I will just do that. So I will remove all this stuff, and case 3b is what I am going to discuss in detail. As you know, the free energy for this will be positive, so it can give you different situations. So let me just draw a figure and explain you. This is 0, this is negative, this is positive, and this is x a, right. This is 1, this is 0, x a. So it can be like this, or it can be like this. As you can see here, free energy is positive and free energy has a curve has a particular shape. It is the opposite to this shape I discussed, correct. So this kind of shapes arise because of clustering in the atoms. To explain it in mathematical terms, let us write down this particular equation in a little nice manner, delta Gm. Let us write down this particular equation in a very nice manner. Let me see how we can write down. Okay, we can write down this like this, n c x a into 1 minus x a plus t n k and multiplied by x a ln x a plus 1 minus x a log of 1 minus x a. where C is what? C is given by this, C is equal to Z HAB minus HA plus HBB by 2. This is what is the equation. So, I can write down delta GM by N taken common. So, this is C into XA 1 minus XA plus TK XA XA ln XA plus 1 minus XA ln 1 minus XA. Okay. So, this is nothing but delta GM star, this is per atom, okay, because you have divided by per atom. So, this is equal to C XA, or let us do one thing, C by KT, and okay, let me just keep it C by KT, this is KT XA 1 minus XA plus XA log of XA 1 minus XA log of 1 minus XA. What I have done is that I have taken KT also out. So, it has become delta GM by KT equal to C by KT into this terms. So, now I can plot this data, this equation nicely. How I will do? I can plot it, this data like this, okay, I will do it here. So, what I am plotting is delta GM by KT, this term, as a function of XB, XA, okay, where XA is 1 here, XA is 0 there. So, if I plot it, let me first check whether I can do it nicely, okay. So, I will plot it for different value of KT by C, for different value of KT by C. Remember, C is also energy term, C is what? Coordination number multiplied by this enthalpy is corresponding to different bonds. So, I will plot for different values of KT by C. So, when KT by C is very high, that means thermal energy term is very high, okay. Let me just see, because otherwise I will make mistakes, those values I do not remember. Okay, let us suppose the value is 1, this is from the textbook actually I am drawing, okay, this is 0 for delta GM by KT. So, when this value is 1, this will look like this. So, when KT by C is 1, this will be like this. Similarly, when the value is 0.5, please follow these curves, 0.5, this will be like this, okay. So, when it will become 0.3, it will start showing very important inflection points, and when it will become 0.3, it will be like this, 0.2325, it will be this, and 0.2, it will be like this. So, that is how actually the curves will change. As you see here, when KT by C is high, means what? Entropic term is dominating. KT by C, KT corresponding to the entropic term, Tk, this one, C is corresponding to the enthalpic term. So, therefore, when the KT by C ratio is high, KT is high, so therefore, entropy term is high. That normally happens when temperature is high. This will be showing a simple solution or liquid solution, and this is what will happen if you add water and kerosene and heat it up to high temperatures, 45 to 55 degree Celsius temperature, they will mix nicely at high temperatures, because this temperature dominated term will be higher than the bond energies. But as you keep on decrease it, when it becomes 1/3, 0.33, you can see here they started showing the miscibility gap, or started showing the difference of different change in the slope of this curve. And when it becomes 0.3, 0.25, already this has shown a hump in the curve. Instead of showing downwards, it is showing upwards. So this is the typical feature of phase separation we seen in case of monotectic or syntactic alloys. So in the monotectic and syntactic alloys, you can explain the formation of these phases, you can explain the formation of these phases very nicely using this formalism very clearly, correct, very easily you can show. High temperatures, it will form a simple solution, liquid solution, all of them are mixed nicely. As you cool it down to lower temperature, below the critical temperature, it will show phase separation or two liquids will be separated, and as you keep on going down, this separation will be increased and finally they will form a liquid solution. So by this formalism, case 3b, I can explain the liquid miscibility gap or monotectic syntactic phase diagram very nicely, that is the idea. Now as you clearly see here, I just don't want to give you a detailed version of that. As you see here, the curve actually undergoes a transition, there is no inflection point here, the two inflection points start forming here, they grow and then become stronger here, you can see the inflection points are developing here, correct. And you know inflection points, what happens, the curvature changes, the curvature of the curve actually undergoes negative to positive or positive negative. So that means at the inflection point the curvature is 0. So therefore if you take this one, at the inflection point, if you take this to be 0, this is double derivative of delta Gm with respect to composition, you will find the critical temperature Tc very easily. Okay. Not only that, at the when this inflection point develops, you will also find that this will be also satisfied, other equation also satisfied. Why? What is that? This one will be satisfied, correct. So by these two equations I can calculate what is the exact composition and the temperature for these separations, or the T critical critical temperature for separation as well as critical composition for separation I can calculate. Well, I will try to do this in next class, but the point I am trying to make is that this theory alone can explain the origin of different phase diagram, because different phase diagram originates due to the change in the free energies. So if you know how the free energies are getting changed, you can explain it nicely how the different phase diagrams will evolve. Okay, we will do the next class, but the next class also I will start a new topic, that is the solid state phase transformations, especially the steels will come into picture, and we will detail discuss about these aspects.